All right, here we go, chapter or section 13.2, which I think you'll find to be pretty straightforward regarding integrals and projectile motion as they relate to this vector stuff. So without further ado, let's get straight into it. We're looking at integrals of vector equations. And you'll see why this is related to projectile motions about halfway through. Now this is very analogous or an easy transition from scalar integrals. In fact, I question whether it even warrants a whole new section, but we'll do it. We'll just go easy on the homework and have a little fun with it rather than beating it to death. We'll jump right in. I'll say that if I've got the integral of some vector function of t, dt, right, r is a vector function, that simply equals big R of t plus some constant. That's it. And this guy here is still an antiderivative. In other words, the integral. And this is important. This is a vector, right? It's not just a constant, right? Because we have to add something in terms of I, j, and k in our regular coordinate system. And then so if we extend, and so this is what would that'd be the indefinite integral. If we move on to the definite integral, it looks even more familiar. I'll say that I might have to spread this over 2 lines, so I'll just be safe, I will. The integral of the same thing, but this time we're going from a to b of r of t is going to equal, well, it's the integral from a to b of f of t. Remember, f was the thing that we applied to the I component, and so that gets stuck with the I, plus the integral from a to b of the g component, or g of t, which is the function we use to describe the motion in the y direction, or j, plus, I bet you can guess it, integral from a to b of h of t, which we described the other day to do the motion in the z direction. So that's it. And remember, because we're doing now a definite integral, we don't have to add this constant because the constant gets subtracted out, just like it did with scalar integrals. So a and b are values of time, values of t. And that's important. That is barely legible. Let's rewrite that here. That looks like scales for some reason. Are values of t. And they're the same, a and b, for the vector function here. When we break it down into much little scalar functions, a and b remain the same for each one of these. That's very important. So I'm going to go straight into an example, and this example is maybe not one you want to skip. So if you are used to skipping examples, this one you might want to follow along. And let's do. The other day I was at the hobby store, and I was looking at radio-controlled glider. All right. And now these gliders, if you know much about sailplanes, kind of the whole game is to find these thermals. So warm air rising. Right, so we have this just bunch of warm air rising like this, and this is going up. And what glider pilots like to do is kind of just stay right on top of this bubble, and they kind of sail up like this in this helix to try to ride. So it's called thermal sailing, versus in the mountains when there's wind blowing up over the mountains, they can just ride the wind up over the mountains. But anyway, nowadays in the toy and radio controlled world, especially this thing called a Wii, you know, that kind of game console or game video stick thing. All right, if anybody knows how those work, it's not magic that that allows them to kind of know. You know, you've got your what they call avatar on the screen as you dance around or punch people or swing a tennis racket. They work with these little solid state accelerometers. All right, so we've got these accelerometers, these little digital, like they sense a force actually, but they call them accelerometers. They're in there, and so we really know only the acceleration of this object. And so from acceleration, somehow we have to figure out where this thing actually is. So let's say we know from accelerometer data gives us, and I'll say that A, our acceleration vector based on time, equals -3 cosine of t I minus 3 sine of t j plus 2k. All right, so again, let's take a step back. What does this mean? 3 cosine of ti minus 3 sine of tj, which means we're probably going clockwise as we look down on the xy plane. And we've got some constant acceleration up, which makes sense because we've got this warm air that's rising like this. You know, I'm going to make that red, make it orange, you know, warm air here. And it's rising up there. And so it's constant acceleration due to this thermal bubble, and then it's going in a circle in the xy plane. All right, well, and I'm I'm standing initially at let's say, what did I say, 300. All right, so 0 here. I'm on the ground. I'm standing 3 meters to the left of my origin, whatever that is in this problem. And then my initial throw is, well, I'll just write it in terms of vectors. My velocity at t equals 0 is 3j. So I throw it in the y direction like that. And my goal now is to find the position vector function r of t. Right. Well, I know that I want to get r of t from my acceleration vector, which is really the same as the second derivative d squared r dt squared. Right? Well, let me write this out. This is so long, it's a hassle to write every time, but I think it's worth doing. So I know that d squared r dt squared equals, and then I'm going to say that is -3 cos ti minus 3 sine tj plus to k. All right, well, I've got the second derivative of my position. Well, the first step I could do is maybe integrate this thing once with respect to t, and then integrate this thing once with respect to t, and let's see what happens. All right, I integrate the second derivative once, and what does that leave me with? That leaves me with dr dt, just the first derivative, and that equals -3, so the cosine, the derivative of that remains negative, so I think that'll be -3 sine of t, I, and then that becomes positive, and it flips to cosine, so +3 cosine of t j, and then that picks up a value of t, or 1 power of t 2t k, plus c, right? It's an indefinite integral, so I've got to add this c in here. Fortunately, I know that this is velocity, so this thing here is that's the velocity. I know that. And I know that at some point when I first throw this thing, it's, oops, that's supposed to be 3j. I really meant that to be a j. 3j equals my initial velocity, so I stick a 0 in here. Well, sine of 0 is 0, so that goes away. Sine of, or the cosine of 0 is 1 times 3, convenient. 3j, and then 2 times 0 is 0, so that goes away, plus c. That makes it pretty easy to see what the vector c is. Vector c equals vector 0. It's 0 in all components. All right, so now I know that dr dt equals -3 sine ti plus 3 cosine tj plus 2tk. And then what I'm going to do with this one, let's integrate it again, still with respect to dt. Integrate this with respect to dt. And I do that integral one more time. And it's equally easy. This time I'm integrating the first derivative, so what I'm going to be left with here is just r of t, which is nice. So now I've got my position. Sine, that turns positive, so I think that turns into, I better check my notes, because I screw this one all the time. Yeah, it stays positive. So this becomes 3 cosine of t, I, and that stays positive, 3 sine of t, j, and I integrate this, right, 2t becomes plus t squared k plus another constant, right? I've got to throw that constant in there. Fortunately, I know where I'm standing at t equals 0. So this is now position. And I know that my position is at 300, right? Or is it? Yeah, it's 300. What did I say on that back page? Yeah, 300. So I know that my 3i plus 0j plus, and I'm still on the ground here, 0k equals 3 times the cosine of 0, which is now 3i, equally convenient. The sine of 0 is 0, so plus 0j, plus the 0 squared is still 0, so 0k, plus d. Well, conveniently, right, d goes to 0. So my vector d, which is my initial position, is, well, my vector d, which I have to add to my initial position, is the vector 0. All right, so that's convenient. So now I know my position vector function, r of t equals 3 cosine of t I plus 3 sine of t j plus t squared k. And so using my initial conditions, my initial velocity, which I knew was 3j, my initial position, which was 300, I can figure out these constants of integration. I can figure out that this c goes to 0 and that this d over here goes to 0. So this is what we've got. And let's put a box around that because it's our final answer. Just like that. Good. All right. And so that's basically integrating in vectors is really pretty much just like integrating in scalars, except that we have to keep the i's with the i's and the j's with the j's, and etc. All right, so let's look at another example. And this one is, I think, an interesting one. I actually went to a talk one time on the aerodynamics of baseballs. So let's take a look at baseball in flight. But of course, we're going to neglect any aerodynamic forces. So we're going to neglect any aerodynamic stuff. So if we draw this baseball here, and so the baseball looks like a sphere, but it's got some, don't baseballs usually have red stitching on them, like that? So the thing is, once this baseball is flying through the air, I don't know much about it, other than the fact that it's always accelerating downward. Even if it's moving up, its acceleration is still down, and the acceleration vector of this thing is exactly, what is it? Negative g j. All right, negative gj. Why is this? This is due to gravity. Okay, so the only thing causing this baseball to do anything different than it is, the only thing keeping it from going in a straight line, is the acceleration due to gravity. And we have to be careful here to define our coordinate system. In this case, I'm saying that we've got a coordinate system that looks like this, where I'm saying that x is in the horizontal direction, y is this way, and z is this way. And if we're careful about how we pick this, I'm going to align my x coordinate with the direction that we hit the baseball. And why is that? Because it makes things easier. So now we know that acceleration, or d squared r dt squared equals negative g j. Okay. Well, what we're going to do with this, we'll integrate this a couple times, and then we'll say integrate, and we're going to do that, but we don't really know. Remember when we did this constant of integration over here? I knew my initial position, I knew my initial throw. So I'm just going to say that the velocity vector at t0 equals, well, let's just call it v0, and that'll have to be a vector. And I know that my position at time 0 equals, well, you know, the right thing to do is to call this R0, but I'm going to say, just for the sake of simplifying this problem a little bit, it really doesn't make it any simpler, just reduces a lot of algebra, which I'm going to say is 0, 0, 0. I'm on the ground, I'm going to put my origin at home plate, assuming that the bat strikes the ball at home plate. And so this is, let's call this home plate. Okay. So now we've got just kind of a generic initial velocity, and we've got a very specific initial position. So let's commence with integrating. Actually, you know what? We're not going to commence with integrating. I'm going to say we're going to integrate d squared r dt squared equals, what is it? Negative g j. And your favorite symbol and mine means that this becomes, and I think this is a good exercise to do on your own, position vector will wind up being 1/2 g t squared j plus v initial t plus our initial, right? But remember that for this particular problem, we're going to wipe this out and say that that is the vector 0. Okay, so we don't have to keep track of that. Okay, just a moment. I'm going to pause for a sec and be right back with the rest of the solution. Okay, so here we're back, and this dot 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 is after much toil, but in some cases this can mean try this at home. They always tell you don't try this at home in these videos, but this time I'm going to say try this at home. See if you get the same thing. It makes sense that you get 1/2 t squared, right? Because the first time you did it, first time you do it, you get just t, and the next time you have to divide by 2. And, so anyway, that's how it works out. But the thing is, we have a j here. Right, we've got this j, which we have to kind of keep track of. But our initial velocity might have a j in it. Okay, so I'm going to write this out, that our initial velocity equals the initial velocity scalar times the sine of some angle alpha plus, and this is times j, plus the initial velocity times the cosine of alpha times I. All right, and what is alpha? If I hit it this way and this is ground and I launch it up that way, this is alpha down there. That's the angle of kind of our initial angle of, not of attack, initial angle, right, of the velocity. So really I've got a j component here and I've got a j component up here, and so this initial velocity gets multiplied by t. So when I rewrite this thing, it's going to look like this. The position vector will look like, let's do the I terms first because that makes the most sense. The only I we've really got is from this thing, and that's get multiplied by the t. So it's v initial cosine alpha t I. So that takes care of the I component, because that's the only I component in this whole thing, is just from the initial velocity. Plus, and then we've got a there's a j component here and a j component here. So I'm going to do this one first just because it's positive. So we'll say that v initial sine of alpha t, right? That takes care of this part and that t. And then minus 1/2 gt squared minus 1/2 gt squared, and this whole thing is going to get multiplied by the unit vector j. Right? So that becomes our projectile motion. So we could do a bunch of, futzing around with this thing, but I think it kind of becomes plug and chug. So I'm just going to cut straight to the chase, and then say the max height for this thing right. When does the max height happen? It happens when the vertical velocity goes to 0, right? Because it's no longer moving up or down. It just kind of slowly reaches this peak, and we could figure that out with a relatively simple calculus problem. But in the interest of time, I'm not going to do that. But this will happen at v sub 0, or so v initial sine alpha. So this becomes the vertical component of the initial velocity squared divided by 2g. Okay, does this make sense? The bigger the initial velocity in the up direction, the higher it goes, right? The stronger gravity is, the lower it goes. But this is squared. It goes up. The maximum height is a function of the initial upward velocity squared. We're going to think about that more in a little bit. The next thing, if you watch, actually in football games, they don't talk about hang time much anymore. Like when a punter would punt the ball, they'd always like time the hang time. There's a little clock in the corner timing it. Maybe they still do that. I just ignore it. But this turns out to be t is 2 times, again, the initial upward velocity, v initial sine theta. This time it's just that, not squared, and it's divided by g. Okay. And last thing is the distance this thing travels. The d is going to be, well, that's a function of v initial squared over g times the sine of 2 theta. Okay, so that one's a little trickier to do. It involves a little bit of trig. You've maybe even done this in physics class, but notice it's a function of velocity squared, right? It's not the vertical component, it's not the horizontal component, it's just the speed squared, right? Why? Because the harder you hit it, it goes both up and it goes farther, right? So that becomes that. But it's the sine of 2 alpha, not the sine of alpha, okay? So we're going to now address a couple questions to think about that are kind of like examples, questions to think about. All right. The first about colon. The first one I want you to think about is when I was a kid, I was into model rockets. And again, I was at the hobby store the other day, so what's on my mind? Hobby type of stuff. Is a two-stage model rocket. Two-stage model rocket. And the two options, option A is to burn, coast, burn, coast, right? So we burn the first stage, coast until we're at the very top, as high as we can coast with the first stage momentum. And then just before the rocket starts to fall, we light the second stage, burn that, and then coast as high as that one goes. So basically we're going twice as high as a single stage rocket would go, right? But let's consider option B would be burn, coast, right? So we don't coast at all after the first burn. We just keep on burning, right? We light up the second one, right after the first one burns out, and then we coast as far as we can after that. And so which goes higher? So between which is higher here? All right, so this is kind of important question 1. And then important question 2 is, what angle will give us the greatest horizontal distance? Right, so that's something to think about too. And I think we'll discuss these in class a little bit, but I want you to think about them before you come to class. Hopefully you get a chance to view this tonight for those fall of 2012. And I will see you in class.